To understand electricity, we must first understand the concepts of voltage, current, and charge. Most of us know that when we rub a PVC pipe with a microfiber cloth, we generate some type of electricity. If we then bring the pipe near a suspended foam ball, the ball is attracted to the pipe. Likewise, if we bring the cloth near the ball is also attracted to the cloth. This may lead us to believe that the electricity in the pipe and the cloth are of the same type. However, this is not the case, for if we touch the ball with the pipe, the ball will get some of the pipe's electricity. However, now, if we bring the pipe near the ball, it is repelled away from it. Yet, the cloth is still attracted to the ball. From this, we see that the electricity in the pipe and the cloth are of different types. We say that the pipe is positively charged and that the cloth is negatively charged. We also see that different types of electricities attract each other and same types of electricities repel each other. If we now wish to find the interactive forces between two charges, we can make use of Coulomb's law. Coulomb's law states that this force is equal to a constant multiplied by the product of the two charges divided by the distance between them squared. But wait a minute, how do we measure the charge of an object? To do that, we must first develop our understanding of current. One of the cool things about electricity is that if we pass electricity flowing in the same direction through two parallel wires, there will be an attractive force between them. With this, we define a unit of current to be the ampere, which is the current required to produce an attractive force of 2 times 10 to the negative 7 newtons per meter of length between two infinitely long wires that are a meter apart. Now we can go about trying to define charge. Let us ask ourselves, which of the below objects should have more charge, the wire or the battery? We might be tempted to say the wire, because it can give off a decent shock of current. However, the battery can give off current for a far longer time than the wire. For this reason, the charge of an object should depend on both the current running through it and how long that current is running for. So, we define the charge as being the current through an object multiplied by the time that that current is on. What if we now decide to connect a battery between two metal plates? Then the right-hand plate will become positively charged and the left-hand plate will become negatively charged. With this setup, we have an electric field that will tend to push a negative charge from the left plate towards the right plate. So, we define the electric field strength as the attractive force that a charged particle experiences in the field divided by the charge of that particle. But how can we define a value for the capacity of this electric field to move charges? We know that if a charge is moved from the left plate to the right plate, then work is done by the electric field on the charge. The value for this work is the force on the particle multiplied by the distance that the particle is moved. However, by rearranging our previous equation for force, we find that the force is equal to the electric field strength multiplied by the charge of the particle. With this, we find that the work done is equal to the electric field strength multiplied by the charge of the particle in the field multiplied by the distance between the two plates. It might now be tempting to define this as the capacity for an electric field to move charges. However, this equation depends on the charge of the particle. So a better definition would be the total work done divided by the charge of the particle. This new value is what we call voltage. By making use of the fact that the work is the change in electrical potential energy, we can define the voltage to be the difference in electrical potential energy between 2 points per charge. With this, we have now developed our understanding of voltage, current, and charge, and can now hopefully understand the concept of electricity better.